Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to do wetland mapping using Earth observation satellite data in Google Earth Engine platform and Python API programming. So, if you are working on the wetlands monitoring, definitely you faced with a lot of challenges for the wetland water bodies detection because the wetlands water body always covered by the vegetation cover, and actually this is a big problem to detect the water bodies below the vegetation cover in the wetlands. So as you can see here, for example in the NDWI image, it is very hard to detect the water bodies while it is covered by the vegetation. So but here, through the wetland index, a conditional equation, I will show you how to detect the whole of the water body while it is covered by the vegetation cover. If you want to learn this procedure, please follow this tutorial and watch this tutorial until end. So, go to the Colab environment and make a new notebook, just like this. This tutorial is really easy to do, and also you don't need to be a programmer. Just you need to have basic information about remote sensing concept and also the Google Earth Engine platform. I will show you how to do the every step from scratch, really easy without any challenge. First of all, in the Python notebook, we need to call the essential libraries to work with Earth Engine functions and capabilities. Let's start with import EE and GEE map. The next library is the Xarray as XR. The Xarray allowing us to convert the data from the image collection to the multidimensional array structure. The Xarray and XEE together bring us this capability. Let's start the programming by run the first cell. Now the notebook is connecting to the server and then start the process. If you faced with any challenge or problem in this tutorial, you can compare my code with yours. The code link is available below this video on my YouTube channel, and then you can open it up and see the every step of programming there. Make another cell and install the XEE. The XEE is one of the main important libraries, allowing us to actually convert the Earth Engine image collection into Xarray structure. It is not built-in available in the Colab environment. That's why we need to install it first. Install XEE and then import. After a few seconds, you will see the message installing collected package and successfully installed. So, in the next step, we need to connect to the Earth Engine account. Earth Engine, authenticate first, start with the authentication. Authenticate your account and then initialize your account information. Just like this. The project name sets to go to the code editor environment in your Google Earth Engine account. Upper right, you can see the account information. Go to project info and here you can find your cloud project name. For example, for my cloud project name is Amir Hussein Ahrari, and also for you it will be another name. So click on done, and the next argument is OPT URL. If you search on a browser about XEE library or Google Earth Engine and XEE, you will easily find a GitHub page including a complete instruction about the XEE library. Here, if you scroll down, there is OPT URL example. Just copy the URL and paste into your code. Let's run. there is a problem. Sounds the EE has no attribute authenticate. There is a typo problem. So the problem is solved, and now Google a Colab asking permission to connect to your Earth Engine account. Permission granted by selecting the Earth Engine account. It's done. In the next step, we need to identify the region of interest. Let's do it by map. GEE map and map. It is a function bring us a user interface in which you can easily identify your region of interest. For example, I'm gonna have a satellite view map. Let's run. There is a Google map here, a satellite view allowing you to identify the region of interest. This tutorial is about the wetlands, and it is important to select the wetland for the sake of a region of interest. So, for example, in the southwest of Iran, near to Persian Gulf here, you can find one of the wetlands, one of the important or transboundary wetlands between Iran and Iraq, this area. So, and this wetland actually considered as my study area. When you see the wetlands, it sounds totally covered by the water, but if you look from the, for example, near infrared band or the other band and also the other electromagnetic radiation bands, you will see that part of the wetland covered by the vegetation cover. So now let's select the area through the rectangle tools. Using the rectangle, I'm selecting the area. Let's make it a little bit bigger to cover the surrounding region. So now I'm gonna have the rectangle as a variable inside the code. The ROI sets to from map, select the last feature. So draw last feature dot geometry. Let's run. And now you can see we have an ROI. It is a polygon including 5 vertices, just like this. In the next step, we need to call Landsat 8 satellite data. So go to the code editor environment and through the search places and dataset, type Landsat 8 collection 2 level 2. Landsat 8 collection 2 level 2. There it is. All the Landsat images or Landsat products listed, tier 1 selected as a main dataset. Open it up into a new page and back to the code. So through the Earth Engine snippet, you can bring this data into Colab environment. Make a new variable, for example Landsat, sets to, make a parenthesis, paste the satellite ID, and then define the filter bounds and filter date. That filter date, I'm gonna make a single clot-free image and then show you how to calculate the different indices and how to assess the situation in this region of interest. So, for example, I prefer 4 years from 2020 to 2024. I'm gonna bring all satellite data for this period of time, the cloud-free one for this region, rebounding to the ROI, and then I'm gonna call those satellite data in which the cloud cover is less than, for example, 45%. So make a new filter, Earth Engine.filter.less than. Satellite data in which the cloud cover is less than, for example, 45%. There it is. And let's print the Landsat to see how many Landsat images available based on these filters. 155 elements available for this period of time. In the next step, I'm gonna make an average image through the time per pixel to make a cloud-free and noiseless image. So here is the Landsat average. Select the Landsat data and calculate the average, just like this. The Landsat average calculated, but remember to select the surface reflectance bands. So dot select all the bands starting with SR, and the rest doesn't matter, just like this, and make a print. Make sure everything is right. We have an average image produced through the time, the average pixel through the time calculated. One of the band is QA aerosol that should be actually removed from the list of the bands. To do this, just enter one additional letter, SRB. In this case, only 7 bands remained, all of them multispectral bands ranging from visible to infrared region of electromagnetic spectrum. So, in the next step, we want to use the Xee library to convert the image format into the Xarray structure. So now, because in the Xarray structure there are a lot of tools for the processing, and also I can handle the process of calculations much easier than Earth Engine. So here I'm gonna make a new data set, XR, the open data set. From Xarray library, I'm gonna make a new data set. The new data set actually gets the Landsat average and convert it into Xarray. Engine should be Earth Engine or EE. The CRS, the coordinate system, EPSG 4326. WGS 84, that is same for all around the world. And the next one is a scale. The scale should be 30 meter. The unit of measurement here is based on degree. 1 degree, 100 kilometer. So 0.003. This is, for example, 30 meter. But 30 meter actually reduce the speed of processing here, and I need to speed up the processing in the tutorial. So that's why I reduced the resolution from 30 meter to 300 meter. As I said, I'm doing this because I'm gonna speed up processing here, but you actually can do it based on 30 meter, but you must be a little bit patient because it takes time when you want to process a data with 30 meter compared to a data with 300 meter spatial resolution. So but for this application, if your region of interest is big enough, 300 meters also works very well. So the next is about the geometry. Geometry sets to the ROI. Let's run a data set, and now a multidimensional structure created. As you can see, the former format, it was an image, stacked of image, different including different bands, converted to an Xarray or multidimensional structure including different variables. Instead of bands, here we have the variables, and also there are 3 dimensions separated: time, longitude, and latitude. So in the next step, I'm gonna actually visualize our study area, this region, from Landsat perspective. So from the Landsat view, I'm gonna actually show how looks like this area in the near infrared and SWIR or shortwave infrared region. So in the next step, make a new cell and now make a new variable for the near infrared band, and also this is the near infrared band and SWIR. From the input data set, as a near infrared is band number 5. Select the band number 5, and the red from the data set, select the band number 4, just like this. Let's run. So now we have two variables, near infrared and red. Let's do the visualization for each. Let me to make a plot structure using matplotlib.pyplot as plt. Let's run, and now I'm gonna actually have two plots next to each other, one of them showing near infrared and another one showing the red band. And also I wanted to visualize the SWIR. Sorry, I forgot it. So ds.sr band number 7. The band number 7 is SWIR2, just like this. So now do the plotting using fig and x. From plt, make a subplot structure. I'm gonna have for example one row with two columns, because I'm gonna have two plots, first column and second column. So one row, two column. So what about the fig size? For example 10 and 5. So plt.tight layout, helping us to actually make enough spaces between the plots. Okay, now let's do the visualization for the near infrared band. Near infrared dot plot. X-axis sets to longitude dimension. Y-axis sets to latitude dimension. And the next one is robust, should be true. Robust helping to avoid outlier impact in the visualization. And the next parameter is axis. I'm gonna show the near infrared in the first axis or in the first plot. Let's do it for the SWIR. SWIR number 2, do the plot with the same parameter. Longitude, define the latitude, robust sets to true, and x sets to second plot. There it is. Let's run a code, and after a few moments you will have new plots. There it is. This is the region of interest from actually Landsat view in near infrared and also the SWIR band. Okay, the range of value is not correct. Actually, the range of values are integer, and we need to do the convert it into surface reflectance values. Okay, you must go a few step back, and now here, after new data set created, we can do like this. The data set multiply to the scale factor that is identified or suggested by the data description, and then plus 2. These are the gain and offsets we are using to convert the digital number values to the surface reflectance. This is a linear equation. Let's run the dataset again. Now the range of value will be between 0 and 1 because of this conversion. After a few moments, you will have a new dataset with a new range of values. Let's run it again. There it is. As you can see, the values ranges between 0 and 1. If you want to make a little bit of space here, it is easy to do. For example, let's add a width pad sets to, for example, 2. Here you can see they are getting a space, they are getting a little bit far from each other. They were too close. Now it looks better. So there it is. This is the near infrared band, and also this is the SWIR. According to the near infrared, as you can see, part of this area covered by the vegetation cover, and we have a higher reflectance in the northern side. But in the SWIR, because it has higher sensitivity to the water content, you can see showing a low reflectance value for this area, meaning that this area is actually covered by water below the vegetation cover. So in this case, if you use, for example, the NDVI and NDWI, you can get a better understanding about this situation. Okay, now I'm going to calculate the NDVI. NDVI sets to, now we already have near infrared and red bands. So the near infrared and red band, the NDVI equation, near infrared minus red, near infrared plus red. So this is the NDVI equation. Let's run, and here it is. This is the NDVI image. Do the plots. X sets to longitude, Y sets to latitude, and robust sets to true. So there it is. In the NDVI image, you can see that most of the area covered by the vegetation cover, although we have water body in this area, but it is covered by vegetation cover, and you can see the index showing the existence of the vegetation cover instead of the water. So let's try with the NDWI, another index specifically used for the water body. So the NDWI, this is a kind of challenges we always face in the wetlands. So the NWIR equals to, for example, NDWIR based on NDWIR, actually the typical equation is based on green and near infrared. So let's define the green band first from the DSSR band number 2 and band number 3 is the green band. So NDWI sets to near infrared green minus near infrared green plus the near infrared. Make plot for the NDWI. X sets to longitude, Y sets to latitude, and robust sets to true. Let's run. So as you can see here, even in the NDWI image, we cannot detect the water bodies with a good accuracy, and you can see that only a part of this area covered by the water body and detected as a water body. So, and the rest of the region identified as a no water area. So this is a typical challenge we always have in the wetland areas, because in the wetland the diversity of the land cover is very high, partially covered by water or covered by the vegetation. But as you can see, the SWIR is really sensitive to the water body, and also shows there is a significant moisture over the region of interest. So in this situation, there are some indices specifically designed for the wetland detection. Recently, I was browsing on the net and I faced interesting paper about introducing WIW for detecting the presence of water in the wetlands using Landsat and Sentinel images. So this paper is available on NDPI website, and also it is open access, and all of the users can reach out to this paper and download it. Just type the name of the paper on the net and find it, and then you can look into the details about this paper. So it's already downloaded on my system, and now I'm looking for the equation to show you. Yes, in the result 3.1 here there are conditional statements based on near infrared and SWIR2 relationship that's showing us how we can identify the water bodies based on reflectance values. As you can see, in this area, in the near infrared and SWIR band, the value of reflectance is very low, and based on these low values we can identify the water bodies by a conditional statement in the easiest as easiest as possible. So now let's do it. WIW. W means WIW stands for water in wetlands or wetland index. It's simpler. So now let's make it the first parenthesis NIR values less than equal than 0.1735 and there is a and here. So but I prefer to use the or, but here based on the instruction first we try with and then we try with or to see how it works. So and here and is WIR2 less than equal the value 0.1 0.1035. There it is. Let's run. WIW calculated. This is a binary image. The true pixels shows the water body and false show the no water body. So let's do the plot to get a better understanding about the situation. Longitude, latitude, no need to robust. So here it is. As you can see, only a part of this area selected as a water body, but still it has a good accuracy because previously we couldn't actually detect the water bodies using NDWI. The result is really better than before, but still we can improve it if you use actually or instead of and here. So let's do it with or condition or operator. This is the or sign, there it is, and let's make a plot. WIW dot plot x longitude, y latitude. Let's run, and you can see the larger area selected as a water body when you use the or, and also when you compare it with the original image, then you can see it has a much better accuracy there. So there it is, and this is WIW index that is really useful for the water body detection where your region of interest covered by the vegetation cover. If you faced with any challenge in the coding and techniques, you can compare my code with yours. The code link is available below this video on the description box. Feel free to share this tutorial with other users and send your feedbacks through the comments. Thank you for the attention.